Welcome back. So, previous lecture we have shown the live demo of digital voltage mode control. In this lecture we are going to show the step for FPGA implementation of mixed signal current mode control with the live demo. So, here we will show hardware setup prototype of digitally controlled buck converter, step for FPGA implementation of mixed signal current mode control, and followed by a live demo of load and reference transient performance. So, we have discussed about mixed signal current mode control in lecture number 75, 76, 77 and 78, all 4 lecture we have discussed in sufficient detail. This is a test prototype of the buck converter, and this is a prototype of the power converter, buck converter, signal conditioning board, and below we will be using FPGA. And these are the buck converter, then we will be using signal conditioning board and the Xilinx FPGA. And you can see this interface and this interface we are actually plugging, because this interface and this interface we are just plugging in onto that. So, that is why that board is not visible. So, this is the FPGA kit that we have demonstrated, and this is connected with the signal conditioning board on the top, just a board to board connector. And this is a picture of the live demo, picture of the hardware setup, and we will be going to a live demo shortly, but I just want to give you a glimpse. So, through computer we are programming this FPGA, and then this actually running the whole converter. So, this is the load transient performance using current mode control, mixed signal current mode control, and the first channel is our 3.3 volt input, that is for for the input to the buck converter, which is these 2 probes, these 2 the supply is connected, is a ground resupply. Then this second supply 10 volt is used to power ADC DAC through regulator and the op amps and so on, and this is the voltage probe to demonstrate in this channel 2, and the current probe is used channel 4. We have in the mixed signal current mode control, what we want to implement inside this logic, inside this. So, you have ADC DAC here, because in mixed signal we require both ADC and DAC, but after this interface when you go to the bottom side of the board, it is the FPGA where we are going to consider this algorithm, okay, and this thing we have discussed in sufficient detail, and the step for implementation is presented in lecture number 57. So, if one can refer for more detail, and in the today also we are going to demonstrate this thing, this step will demonstrate in actual hardware prototype. And the code, this is the main code mixed signal current mode control. This Verilog code have been explained, we have explained this Verilog code I think lecture number 76 in detail, and we have considered different sub module for this, one clock, one digital PI controller, one current reference, one PWM with date time, and one with the USAVE file, which is to define the IO pins. So, this code, main code is divided into 3 pages, because it is a long code, and then we have, so this code of this main code of mixed signal current mode control is explained already in lecture number 77, I believe 76, and then the clock generator circuit we have presented both for digital and current mode and voltage mode control for both in lecture number 72 and 76. So, I am not going to discuss this again. Digital PI controller I think we have demonstrated in lecture number 77, we have discussed. So, we are not going to discuss, but this is just a screenshot, and then the current reference generation we have discussed in lecture number, I think it is lecture number 76 that we have discussed, and what are the block. Then PWM date time circuit we have discussed in lecture number 76. Yeah. Now, this is the user constraint file. So, that means this user constraint file is to, you can see all these address are given. So, this ADC vector 10 bit ADC, 12 bit DAC, then it will also have a load Q load address, then transient type through a switch, and we will also consider a comparator here. This is a clock, and I think this comparator should be enabled. So, I do not know, it should be enabled here. And then so this is enabled, sorry, this is the right file, I think the earlier was not the write file. So, this is the write file, programmable file, because only what was disabled, this is now enabled for this COM. And next, this is what we are going to demonstrate now. That means, this is a picture of the prototype that we are going to consider. So, now we are going to the live demonstration. So, now we are going to demonstrate mixed signal current mode control. Actually, this is a part of this lecture where we have already shown using screenshot of what are the steps for, first of all we discuss in detail about the Verilog code for implementing mixed signal current mode control in 8th week, and in this lecture we have demonstrated what are the steps, that user constant file, then main module, sub module, how to instantiate, then we have shown how to dump this code into our FPGA. So, I am not going to repeat that, it has already been dumped. Now, we are going directly to the hardware. So, this code is running. Now, we are turning on the power supply, 3.3 volt is the input, and we are making first, let us say we are making load transient. So, this is a load transient where again we are changing the load current from So, load current was initially the resistance was 13.5 ohm. Now, we have made a load step transient. How? We have added the parallel resistance is 0.33 ohm with the 13.5 ohm. So, effectively it was becoming like 0.32 ohm. So, this has created a load step of roughly 3 ampere. So, it is going, you can see the current load step happening, and because of load step of transient there is a voltage undershoot, and if you just stop it, you can see the voltage undershoot at 3.3 volt input, and then there is a followed by load step down transient. So, we got reasonably good transient response, but we are going to design actually current mode control in the subsequent lecture in the 11th week, but here we have considered some reasonably, I think, good parameter of the Kp and Ki, which we have presented in the class, but we will show the steps for design in the 11th week, the lecture in the 11th week. So, now this is the load step of transient, load step transient. Now, we have a switch provision we have discussed. If you change this switch position, it is making a reference transient. So, in the reference transient, if you trigger it, I want to show that this is for first it is going to step up reference transient where it is changing from 11 volt, because 1, 2, 3, 4, 5, 1 volt. So, that means the 5 division, 1 division is for 0.2, you can see 0.2 volt. So, 1 volt to 1.1 volt step up transient followed by the step down transient, and this is the current overshoot during step up and current undershoot during step down transient. So, this is the response of current mode control, and since the reference is generated from inside, so this has, I mean, there is no such delay, so it responds almost immediately, and because of this finite output impedance, because we cannot make the closed loop faster than 1/5 or 1/6 of the switching frequency called closed loop bandwidth, because we also discuss about the small signal validity. So, this is what about the mixed signal current mode control. Now, we are going back to our class. So, just now we have completed, we have shown the live demo of the mixed signal current mode control, where we have discussed hardware setup, prototype of a digitally controlled converter. We have demonstrated step for FPGA implementation through a live demonstration, and we have seen the load and reference transient performance. That is it for today. Thank you very much.